Before diving in, one honest correction, because it matters for getting this story right. The actual breakthrough at the center of this story didn't come from the James Webb Space Telescope. Webb had already tried, years earlier, to detect this specific planet's atmosphere and came back with results too ambiguous to draw a firm conclusion from. The discovery that actually confirmed it came from a ground-based telescope in Chile using an entirely different technique. That distinction matters, but it doesn't make the underlying story any less remarkable. In July 2026, a team of astronomers announced they had found something that had never been confirmed before in the entire history of exoplanet science. A genuine, verified atmosphere on a rocky planet sitting inside the habitable zone of another star. Not a hint, not a statistical maybe, a real confirmed detection described by the scientists who found it as a major turning point in the search for life beyond Earth. This is the real story of LHS 1140b, the planet that finally answered. A question astronomers have been asking for 20 years. Why it took a completely unexpected detection method to crack it, and what James Webb's actual, honest role in this story turned out to be. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why confirming an atmosphere on this specific kind of planet counted as such a genuinely significant milestone, you first need to understand exactly how difficult this particular question has been for astronomers to answer, and how long it's actually been sitting unresolved. Robin Wordsworth, a professor of environmental science and engineering at Harvard and one of the researchers involved in this discovery, laid out the history of the underlying question directly. 20 years ago, he explained, scientists wondered whether other terrestrial-type planets even existed at all. Then, astronomers learned they're actually common throughout the galaxy and found some sitting within their stars' habitable zones, the specific range of orbital distances where surface temperatures could theoretically support liquid water. The next question, Wordsworth explained, was whether any of those rocky, habitable zone planets had actually managed to hold onto an atmosphere. Now, he said plainly, we know at least one has. That specific sequence, existence, then habitable zone placement, then confirmed atmosphere, represents three genuinely distinct, increasingly difficult milestones in exoplanet science, each one built on the last, and each one considerably harder to achieve than the one before it. Astronomers have now identified thousands of confirmed exoplanets, including a genuine handful of rocky worlds sitting within their stars' habitable zones. But confirming whether any of those specific worlds actually retained an atmosphere, rather than existing as a bare, airless rock the way Mercury does in our own solar system, has remained one of the single most difficult, most persistently unresolved challenges in the entire field, a challenge that had simply never been successfully cracked before this specific discovery. The planet at the center of this story, LHS 1140b, sits roughly 48 light-years from Earth, orbiting a red dwarf star within that star's zone. It wasn't a new or obscure discovery. Astronomers have been studying this specific planet closely for years, precisely because its combination of rocky composition and habitable zone positioning made it one of the most promising, most closely watched targets in the entire search for potentially habitable worlds beyond our own solar system. Earlier research, including a study published in July 2024, had already proposed that LHS 1140b might be a genuinely promising super-Earth, potentially covered in ice or possessing surface oceans, based on modeling of its size, mass, and orbital characteristics. But proposing a plausible scenario based on modeling is a fundamentally different thing than actually confirming it with direct observational evidence, and that confirmation had remained stubbornly out of reach. This is exactly where James Webb's real, honest role in this story comes in, and it's worth being precise about it rather than either overstating or erasing it entirely. Webb had already attempted to search for atmospheric signatures on LHS 1140b, along with several other rocky, potentially habitable exoplanets, using its own spectroscopic instruments. According to the research team's own summary of that prior work, those observations came back inconclusive. Not a confirmed detection, but not a confirmed absence either. Simply an ambiguous result that didn't settle the question one way or the other. That's a genuinely honest, unglamorous outcome, and it's worth sitting with for a moment because it illustrates something important about how real science actually works. Even the most powerful telescope ever built doesn't automatically produce a clean, definitive answer to every question researchers pointed at. Sometimes the signal is simply too faint, too easily confused with noise or with other unrelated sources of variation, for even Webb's extraordinary sensitivity to resolve with confidence. Faced with that inconclusive result, a research team led by Colin Cherubim, who recently completed his PhD in Earth and Planetary Sciences at Harvard University, working alongside his joint advisors, David Charbonneau and Robin Wordsworth, took a genuinely different approach entirely, one that didn't rely on Webb's own instruments at all. Rather than trying to directly detect specific gases within LHS 1140b's atmosphere through the conventional method, transmission spectroscopy, which involves measuring how starlight filters through a planet's atmosphere as it transits in front of its star, Cherubim's team focused on something else entirely: helium, and specifically helium in the process of escaping the planet's atmosphere and drifting outward into space. Understanding why the team chose this specific, unconventional approach requires understanding a genuine technical limitation that has hampered atmospheric studies of small, rocky exoplanets for years. Most atmospheric gases, when researchers try to detect them through transmission spectroscopy, produce signals that are extraordinarily faint and easily confused with noise, especially for a planet as small as LHS 1140b, orbiting a star as faint as a red dwarf. Helium, however, behaves differently. Once helium escapes a planet's gravitational pull and begins drifting outward into the surrounding space, it can be detected at a considerably greater distance from the plane T than most other atmospheric gases, spread out across a much larger physical volume, which makes its resulting signal genuinely easier to isolate and confirm, even for a planet this small and this faint. Cherubim's team developed a detailed theoretical model, specifically predicting that if LHS 1140b genuinely possessed an atmosphere, its upper layers should contain substantial amounts of helium slowly leaking away into space, and that this escaping helium should be detectable using the right instrument, pointed at exactly the right moment. To actually test that prediction, the team turned to the warm infrared Echelle spectrograph, known as WINARID, mounted on the Magellan Observatory in Chile, an entirely ground-based instrument working from the surface of Earth rather than from space. The team caught a genuinely fortunate break in the timing of their observation. On the specific night they conducted their study, LHS 1140b happened to transit in front of its host star at the same time as a second separate planet in the same system, giving researchers a rare direct opportunity to observe both worlds under identical conditions on the same night, using the same instrument, and then directly compare the results. That second planet showed no sign of an atmosphere at all in the resulting data. LHS 1140b, by contrast, produced a clear, unambiguous signal of helium actively escaping from the planet into space, direct, confirmed evidence that this specific world still retains a genuine atmosphere. Cherubim summarized the core significance of the finding in the most direct possible terms. An atmosphere is essential for a planet to support life as we know it, he explained, and this is the first time anyone has found an atmosphere on a rocky planet in the habitable zone of another star. That's not a hedge, and it's not marketing language. It's a precise, technically accurate description of exactly what had, and hadn't, been accomplished by any previous research anywhere before this specific study. It's worth understanding just how much genuine scientific skepticism this particular research plan faced before it actually succeeded, because that skepticism is exactly what makes the eventual result so credible. David Charbonneau, the head of Harvard's Department of Astronomy and one of Cherubim's joint advisors, was candid about his own initial doubts. The underlying prediction had come entirely from a mathematical model, and this specific type of helium escape signal had never previously been observed from any rocky exoplanet at all, anywhere, by any research team. Charbonneau openly admitted that he had genuinely doubted whether the plan would actually succeed going in. What changed his mind was watching the process play out directly. Cherubim analyzed the planets already known in this system, predicted specifically that LHS 1140b would show a helium atmosphere, then personally organized the necessary telescope time, gathered the actual data, and the resulting detection turned out to be, in Charbonneau's own words, statistically rock solid. That specific sequence, a testable, falsifiable prediction made in advance, followed by a dedicated observation specifically designed to test it, followed by a result strong enough to convince even a genuinely skeptical senior researcher, is about as close to the scientific method working exactly the way it's supposed to as you're likely to find in any single research story. It's also worth appreciating what this discovery demonstrates about the broader toolkit now available to astronomers studying rocky exoplanets. According to the research team, this result indicates that astronomers may now be able to study the atmospheres of rocky exoplanets from the ground using dedicated searches for gases actively escaping into space, rather than relying exclusively on space-based telescopes like Webb and the far more technically demanding transmission spectroscopy method that had produced inconclusive results for this same planet just a few years earlier. There's a genuinely important additional piece to this discovery that goes beyond simply confirming an atmosphere exists at all, how long that atmosphere has actually survived. Based on their combined analysis, the research team estimated that LHS 1140b's atmosphere has likely persisted for more than 3 billion years, an extraordinary span of time for a rocky planet's atmosphere to survive intact. particularly given that the planet orbits a red dwarf star, a category of star known for being considerably more magnetically active than our own sun, particularly during its early life, prone to powerful stellar flares and intense radiation capable of gradually stripping away a smaller planet's atmosphere over time. Finding an atmosphere that has apparently survived billions of years of exactly that kind of stellar bombardment makes LHS 1140b a genuinely exceptional and genuinely promising target for continued study, exactly the kind of long-term atmospheric stability that would matter enormously if this planet turned out to host anything resembling life. It's worth being completely honest and precise about exactly what this discovery does and does not actually establish, because that precision is exactly what separates genuinely remarkable science from an overstated headline. Confirming that LHS 1140b has an atmosphere is not the same thing as confirming that it's habitable, and it's certainly not evidence of life. The current detection specifically identified escaping helium, a single, individual gas, rather than a complete chemical inventory of the planet's atmosphere. Cherubim himself has been direct and appropriately measured about exactly what comes next, describing his hope to identify the atmosphere's full chemical composition in future observations, and eventually working to determine whether the planet actually has surface oceans or other features genuinely connected to habitability, rather than treating the current helium detection as a finished, complete answer. This has been a model validation, he explained, and hopefully it's just the first of many more observations still to come. That framing matters enormously, because it places this discovery accurately within the broader, ongoing arc of exoplanet research, rather than presenting it as a final, complete conclusion. Cherubim and his colleagues have already stated their intention to use this same predictive model and the same underlying helium escape detection technique to search for atmospheres on additional rocky, potentially habitable worlds beyond LHS 1140b specifically, treating this discovery as a genuinely validated proof of concept for a broader, repeatable research method, rather than a singular, isolated result. It's worth placing LHS 1140b's confirmed atmosphere within the much broader context of everything else astronomers have learned about rocky exoplanet atmospheres in recent years, because the picture that emerges is considerably more nuanced and considerably more scientifically interesting than a simple story of confirmed success. This same general period has produced a genuinely striking mix of results across different rocky worlds, some retaining atmospheres under conditions nobody expected, others confirmed to have none at all despite initial hope. In May 2026, Webb's own observations of LHS 3844b, scorching tidally locked super-Earth roughly 48 light-years away, confirmed the opposite outcome entirely. A dark, barren, genuinely airless rock, with a permanent dayside, hot enough to melt metal and absolutely no detectable atmosphere at all. A direct, sobering counterexample demonstrating that proximity to a habitable adjacent category of star doesn't automatically guarantee a planet retains any air. In March 2026, a separate Webb study found the opposite kind of surprise on TOI 561b, an ultra-hot rocky planet completing a full orbit in under 11 hours. Conditions researchers had generally assumed should be far too extreme for any atmosphere to survive at all. Instead, Webb found strong evidence of a thick atmosphere, sitting above what researchers described as a churning global magma ocean, leading lead researcher Johanna Teske, a staff scientist at the Carnegie Earth and Planets Laboratory, to describe the planet as behaving like a wet lava ball, a genuinely strange, volatile-rich world that appeared to be actively recycling gases between its molten interior and its surrounding atmosphere. Taken together, these results paint an honest, genuinely complicated picture of rocky exoplanet atmospheres, one considerably richer than a simple binary of habitable versus uninhabitable worlds. Some rocky planets, even ones sitting in conditions that seem outright hostile to any atmosphere surviving at all, turn out to retain thick, genuinely active atmospheres. Others, sitting in conditions that seem, on paper, considerably more favorable, turn out to be completely airless. And now, for the first time, one genuinely promising habitable zone world has been confirmed to retain an atmosphere that has apparently persisted for billions of years, exactly the kind of long-term stability that matters most for any serious discussion of habitability. This also connects to a broader pattern worth understanding honestly: the search for atmospheres specifically within the TRAPPIST-1 system, one of the most extensively studied groups of rocky, potentially habitable exoplanets discovered to date, has produced a string of similarly inconclusive or negative results over the past several years, adding real context to why LHS 1140b's confirmed detection represents such a genuine milestone, rather than simply one more data point in an already crowded, straightforward field. Webb's earlier observations of planets within the TRAPPIST-1 system, gathered as far back as September 2023, have repeatedly failed to produce a confident, confirmed detection of any atmosphere at all on any of that system's rocky worlds, despite years of dedicated observation time and genuine scientific interest, precisely because red dwarf stars, the category TRAPPIST-1 belongs to, tend to be considerably more magnetically active and prone to stripping away a smaller planet's atmosphere than researchers had originally hoped when this system was first discovered. That accumulated pattern of inconclusive and negative results across one of astronomy's most closely studied planetary systems makes LHS 1140b's confirmed positive detection considerably more significant by comparison, a genuine break in a string of otherwise discouraging results. It's worth stepping back and appreciating the actual honest significance of this discovery within the much longer arc of exoplanet science as a field. Since the first confirmed exoplanet discovery in 1992, astronomers have progressed through a genuinely logical, if sometimes frustratingly slow, sequence of increasingly difficult milestones. First confirming that planets beyond our own solar system exist at all, then confirming that rocky, Earth-sized planets specifically exist, then confirming that some of those rocky planets sit within their stars' habitable zones, and now finally confirming that at least one of those rocky, habitable zone planets has actually managed to hold onto a genuine atmosphere across billions of years. Each of these milestones took years, sometimes decades, of dedicated observational effort to achieve, and each one narrows the search for a genuinely Earth-like, potentially habitable world just a little further, ruling out entire categories of otherwise promising candidates while simultaneously validating others. So here is where this genuinely, honestly stands, based entirely on peer-reviewed research published in the journal Science on July 16, 2026, and the direct, on-the-record statements of the researchers who conducted this work. LHS 1140b, a rocky planet sitting within the habitable zone of a red dwarf star 48 light-years from Earth, has become the first rocky, habitable zone exoplanet ever confirmed to retain a genuine atmosphere, detected not through James Webb's own instruments, which had previously returned inconclusive results on this exact question, but through a ground-based detection of helium actively escaping the planet's upper atmosphere, observed using the Magellan Observatory in Chile. That atmosphere appears to have survived for more than 3 billion years, despite orbiting a star category generally associated with intense atmosphere-stripping radiation, making LHS 1140b one of the single most promising targets currently available in the ongoing search for genuinely habitable worlds beyond our own solar system. This is not evidence of life, and the researchers themselves have been careful and direct in saying so, describing this result as a model validation and a foundation for further study, rather than a finished, complete answer. That is not manufactured drama built around an exaggerated headline. That is the honest, carefully documented, genuinely significant record of exactly how a 20-year-old scientific question, whether any rocky, habitable zone planet beyond our own solar system had actually managed to keep its atmosphere, finally got its first confirmed answer. If this kind of story is what you come here for, one grounded in exactly what real astronomers measured, confirmed, and correctly attributed, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly more genuine progress waiting in the search for another Earth. Drop a comment telling me whether you think LHS 1140b will eventually be confirmed to have oceans, and share this with someone who still thinks every exoplanet discovery gets credited to the same one telescope.